Thank you. So thanks. I'm here actually because Tanya Regimbo couldn't attend, so I will take over her slot and present work that we have done in collaboration with people from the LIGO and Virgo collaboration, so Tanya Regimbo and Sachdev, and with some theories in ANSI and Torino, so Alessandro Cuoco and Pasquale Serpico. So this is about how we can use the cross correlation with galaxy catalogs and gravitational waves in order to unveil basically the origin of the binary mergers. Okay, so just a bit of short introduction to the cross correlation, how we can basically use the two-point correlation function in order to define what is the probability of finding generally a pair of an object from a given population A in a given volume 1 with a population, an object from a population B in a volume 2. So there is this probability is finite, and it is related and relies on the possibility of having an excess of cross correlation between the two populations, which is this quantity xi here. And xi is nothing else than the two-point correlation function, which relates the density fields at a given position. And this is the two-point correlation function in real space. But usually we do work actually in Fourier space when we have discrete objects. Then the number density fluctuations for a given population can be written in terms of basically a factor that relates the number density fluctuation for a given population to the number density of the underlying matter distribution. And this factor here is what is called the bias factor, and indicates to which extent the field I in which we are interested in, or for which we have tracers, is a good proxy for the matter distribution in the universe. So because any time we have some tracer, or no matter what kind, there is always some kind of bias that we have to account. So there will be dedicated talk about cross correlations on Saturdays by David Alonso and Stefano Camera. So I won't go into much more details about the formalism. Just a sketch on how cross correlation has been used so far in high energy astrophysics in order to unveil the link between large scale structures and other type of cosmic backgrounds. So those are typical maps of cosmic backgrounds that we do have at our hands. So this is a map of the photons collected by the LAPTh telescopes, which is a satellite aboard of the Fermi satellite, and it actually scans the sky at GeV to TeV energies. This is one of the very first images of the in X-rays by E Rosita, which is giving us exquisite angular resolutions in order to resolve all the structures, either in the galactic disk, but also at higher latitudes, and an unprecedented view on the X-ray extragalactic sky. This is a map of the weak lensing measurement, how we can really, basically this is basically the mostly unbiased tracer of matter distribution in the universe. And we do have their measurements thanks to the DES survey. And here is just an example of a galaxy catalog from the 2MASS. So how cross correlations between those different methods has been used. This is just a few examples of how we have been doing that. I think Stefano will go into more details on this, but cross-correlating Fermi-LAT photon data with galaxy catalogs, people have found a positive cross-correlation at scales of about a few degrees. And this can be interpreted in terms of several astrophysical populations like blazars or star-forming galaxies, but it might also actually hide kind of signal from dark matter. And so this kind of cross-correlation studies have been used and are a powerful tool for indirect dark matter detection. The same is true when you cross-correlate the isotropic Fermi-LAT sky with with lensing. And again, the works, I think this is the first work really finding a positive cross correlation between the two catalogs, or the two, let's say, images. And again, you can use it to leverage onto the properties of dark matter. But you can also use cross-correlation to try to have an hint on other type of dark matter candidates, as for example, if you go to, this is a projection for the cross-correlation of E Rosita with galaxy catalogs, and then besides having again the contribution from astrophysical sources like galaxies and active galactic nuclei, you might also have some contribution from stellar neutrinos, and you can use again this cross-correlation technique to get constraints or even detection of this type of LSE matter in the universe. So if we come then to the topic of my talk, this is really about cross-correlating galaxies with gravitational wave events. And in this respect, this kind of techniques is really an example of the synergy between cosmology and multi-messenger astronomy. So the cross-correlation with large-scale structure and gravitational wave has been used in the past for three main broad applications, and I will review them in partly. So the first application, also Chiara mentioned that this morning, giving a quite broad introduction, is how we can use gravitational waves to infer cosmological parameters. So in this actually rely on the fact that gravitational waves are say objects, generating objects are standard sirens, so we can get a direct measure of the luminosity distance for the sources, which however lacks redshift determination. So how to assign a redshift to a given gravitational wave event? This has to rely either on the direct association with electromagnetic counterparts, for which we can then fix the redshift and measure it, or through statistical galaxy association, where the overdensities and underdensities around the gravitational wave source within its localization volume are studied, and giving a probability of the galaxy to actually being associated to the gravitational wave event. And finally, a third method actually relies on the cross-correlation. So what one can do, and people have done so, is try to cross-correlate galaxy catalogs and gravitational wave events, because in this respect, you don't really need an electromagnetic counterpart to define the redshift, and is actually even more efficient when it's more efficient than other methods when you have a poorly localized event. So to do so, you basically take your catalog of gravitational waves and the catalog of large-scale structures, and you try to find a positive cross-correlation that you do expect if gravitational wave sources, as it is thought, are sitting in galaxies, and so there should be a positive cross-correlation with the underlying galaxy distribution. As I said in the introduction to the cross-correlation formalism, the density field, either for the galaxies or for the gravitational wave, is biased with respect to the matter distribution. And this factor here, which is the gravitational wave bias, is also something which, as it is the case for galaxies, evolves with redshift. So one can do, and what people have done, is to make forecasts on how good we can reconstruct cosmological parameters, like, for example, omega matter and H0, together with the gravitational wave bias parameter, so the normalization and the redshift dependence of this bias. And in this case, you can, people have shown that you can get quite precise measurements of H0 and omega matter with future surveys, and there is actually a strong correlation between, for example, the normalization of the bias and the evolution with redshift. Another, along this quite same direction, you can exploit the cross-correlation of gravitational wave events with galaxies in order to try to disentangle or discriminate different formation mechanisms for the binaries that leads to the gravitational wave events. So as an example here, this is the cross-correlation power as a function of multiple that you would expect from two different formation scenarios for the binaries that leads to gravitational wave events. Either that comes from stellar evolution, so as an endpoint of the stellar evolution, you will have basically astrophysical binary black holes, or the binaries can also have a primordial origin. And the point of several works that have been performed in the past was to try to leverage on differences that may exist in the bias that you expect for those different formation mechanisms. So in particular, it is actually one possible mechanisms that can lead to the formation of primordial black holes is through the collapse of large density fluctuations in the very early universe. These would form what are called primordial black holes that eventually in some part of the parameter space, they can also account for the totality of dark matter in the universe. And because those primordial black holes have been formed predominantly in small halos, then the binaries that would form by their interaction would be less biased with respect to the matter density distribution. And so the bias that is predicted for this kind of scenario for binary formation is less than 1. On the other hand, if you have gravitational wave events that comes from the endpoint of the stellar binary evolution, so astrophysical binary black holes, then this tends to form and to occur in very heavy halos. And so those would be, again, bias tracer of the matter distribution, but with a bias factor larger than 1. And trying to leverage on this difference of the bias through the cross-correlation analysis, people have tried to make forecasts on how we would be able to distinguish those two formation mechanisms in the future with a joint analysis of the cosmological parameters. And in this respect, those kind of analyses have been shown to be only marginally able to discriminate between scenarios, but partly part of the reasons is because they really try to join, to make a joint determination of the cosmological parameters and binary black hole bias. So finally, another way to exploit the cross-correlation in the literature has been not by cross-correlating galaxies with the gravitational wave events, but with rather the gravitational wave background. So there should be a background of gravitational waves that is generated by gravitational wave events that are too faint to be or not so loud to be detected by the interferometers. And so they would contribute as a superposition of a correlated noise in the detector. And this is what usually is called the stochastic gravitational wave background. So one way to highlight and try to unveil its properties is again through cross-correlation, because if it is of astrophysical origin, the clustering of the galaxies should be related to the position of the gravitational wave events that are superposed in order to produce this background. And so there should be a positive cross-correlation between this gravitational wave background of astrophysical origin and the large-scale structure. One of the technical details to understand, and this is what people have investigated at first, was are we really able to surpass the limit of the shot noise in order to be able to detect this kind of correlation. And apparently the answer is yes, that you can exploit cross-correlation with very dense and quite numerous galaxy catalogs in order to basically beat the shot noise and be able to find a positive signal to noise for the cross-correlation. This is very much more promising than using only autocorrelation. And in this very same spirit, it has been shown that you can then use the cross-correlation in order to constrain the power emitted by those unresolved gravitational wave events as a function of redshift, and perhaps also get some hints on the nature and the different formation mechanisms. So then coming to the details of our work, what we wanted to understand in a more quantitative and more realistic way than what was done so far has been to try to answer the following question. So when and under which circumstances will we really able to measure the cross-correlation between binary events and large-scale structure? And this requires on the one hand to make realistic Monte Carlo simulations of different binary matter populations, so binary black holes, binary neutron stars, and binary black holes neutron star systems, but also to model the selection effects for specific detector configurations and use really a full pipeline of reconstruction of the signal within the detectors under different configurations of the detectors themselves. And on the other hand, it also requires to have realistic modeling of what galaxy catalogs are currently available and what will be available in the future. And here, let me just point to a very kind of not so marginal detail, because here really the aim is to understand to which precision we can measure the bias. And so we do fix the cosmology to the Planck-Best fit, and we will see that this makes of course, the projection more promising than what was found in the past. But we also know that for the moment, gravitational waves are not really competitive in terms of error budgets in determining the cosmology with respect to CNV experiments. So we do fix the cosmology to the Planck-Best fit. So, and the answer is that you can measure the cross-correlation of different binary populations with large-scale structure with 10 years of data and design sensitivity already with 5 detectors of second generation. And the game changer here is really, on the one hand, the galaxy catalog optimization to the problem at hand, and on the other hand, a tomographic approach. And the rest of my talk is dedicated to explaining how we can really do that and what are the subtle details behind the analysis. So in order to work with the cross-correlation, we work in multiple space with the cross-angular power spectrum. Here are those CLs that relates the different catalogs A and B through those quantities, which contains the information about the redshift distribution of the objects, the spherical Bessel functions that takes into account the expansion of the universe, and finally the relative density fluctuations in Fourier space, which are directly related to the matter density fluctuations through the bias. One can rewrite that under some approximations in terms of the nonlinear matter power spectrum of large-scale structures, kind of window functions of the field I, so one of the 2 catalogs, and the bias with respect to the matter distribution. So if we are interested in correlating, let's say, galaxy catalogs with gravitational wave events, then for galaxy catalogs, the window functions are known, and the bias can be also determined at, let's say, 10% precision by the catalog, from the catalog itself, while for gravitational wave events, again, the window function will be known, and we will run mock data. I will show you how. However, the bias is actually the unknown of our study, and we do fix it to a reference which is a bias equal to 1, but anything I will say in the following does not really depend on the reference model taken for the bias. Of course, you can measure this cross correlation. You can also measure it with a given error, and the error depends on the sky coverage of your catalogs. So basically, how large is the field of view of your catalog at end, and depends on the shot noise. So you can beat, as I said, the Poisson noise if you have a catalog with a lot of galaxies that are detected, or a lot of gravitational wave events that are detected. And here, this W factor is an approximation from the shape of the beam, which we do assume it is Gaussian, and I will comment on that approximation later on. So while for the catalogs of galaxies, we can take real catalogs, and as I will explain, for the gravitational wave catalogs, what we do use here are actually Monte Carlo simulations that were developed for the Einstein Mod data challenges, where for each class of binaries, we simulate the redshift distribution starting from a redshift probability distribution function, where the merger rate densities follows the star formation rate weighted by some time delay function, and this merger rate density is normalized to the local rates as inferred by the first two LIGO-Virgo observation runs. So just to go a bit more in the details, we have to extract for each class of binaries the masses for a given distribution. So a Gaussian mass distribution from the binary neutron stars, a power law mass distribution from the BBH. And since this work was done prior to the discovery of the black hole neutron star first events, we had a fixed and component masses for this type of binaries. And the rates are not updated to the latest discoveries. And in particular, I want to just mention that this, for the black hole neutron star systems, it's just an upper limit as it was in 2019. We also extract from uniform distributions the orbit inclination, the polarization, and the phases merger, because we want really to simulate the full events that we would generate, and then let them pass through the detector response function and reconstruct what is the signal to noise ratio for this matched filtered detection pipeline. And we do so for 3 different detectors configurations. So we have the case of HLD, so 2G detectors at the 3 LIGO and Virgo site with the sensitivity that is the LIGO-Virgo design sensitivity. Here you can see that we have about 500 binary neutron stars, 4,000 binary black holes, and kind of similar numbers for the black hole neutron stars. But what is also really important here for any cross-correlation study is what is the distribution of the redshift distribution of the events. So this is the number of events as a function of redshift that would be detectable by this configuration of detectors for SNR larger than 8 and for 10 years of data and 80% duty cycle. So what you can see is that binary neutron stars and black hole neutron stars events are all cosmologically very close, the detectable ones, while binary black holes extends to higher redshift and they are peaked at around the redshift of 0.3. The second configuration of detectors that we have considered is 5 2G detectors, 3, so the LIGO-Virgo detectors, adding LIGO-India and KAGRA, always at design sensitivity. From the point of view of the statistics, this is increased by a factor of around 5 with respect to HLV. And also the redshift distribution is very similar to the 3 detectors configuration, but the distribution of, in general, the redshift distribution extends to slightly higher Z. And what is most important is that for binary black holes, the sample is almost complete. So it means that all black holes binaries are detectable within a redshift of 0.3. And finally, we do consider a futuristic scenario of having one Einstein telescope, so one 3G detectors, one Einstein telescope, and 2 cosmic explorers at the LIGO and Virgo sites. And in this respect, the statistics is very much increased by orders of magnitude. So we have more than 10 to the 6 events for BNS, 10 to the 5 for binary black holes, and about 10 to the 6 again for binary black holes neutron stars. And as for the redshift distribution of detectable objects, then those are all peaked at around the redshift 1 and extend even to higher redshift with a tail that extends up to 5 or 6 in redshift space. And one remark is that for binary black holes, since this sample was already complete up to redshift 0.3 by the 5 detector configuration, this is of course still true for the 3G configuration. And so we expect about 6,000 objects within redshift 0.3. So as I said, we really try to be realistic in the detection pipeline. And we also run BBH-LSS, which is a fast Bayesian position reconstructing algorithm that on the one hand gives us the localization probability sky map. So for each event, we can get what is the localization error and the confidence area of this localization. And then we can also get the posterior probability for the luminosity distance. So then what is relevant for the cross correlation is, first of all, what is the error on the luminosity distance and henceforth on the redshift, because we fix the cosmology. So from the luminosity distance, we can get directly the measurement of the redshift distribution. And so we wanted to investigate what is the error that we have in the determination of the redshift. And here I'll show that for the 5 detector configuration and 2G detector configuration and the 3G detector configurations for binary black holes. So the error is around 20–30% in the reconstructed redshift, and against some like naive expectation that is also used sometimes in the literature, the signal over noise doesn't really scale as 1 over the SNR. So the error doesn't really scale as 1 over the SNR for most of the samples. So the dependence on the SNR of this error is pretty flat, at least for the 5 detector configurations, while for the ET2CE, then you have kind of double modes. So one which is mildly dependent on the SNR for the redshift error, and one that instead has this expected behavior on 1 over the SNR. And this is important for us for cross-correlation purposes. So for black hole neutron stars, we do assume basically the same performances as black hole binaries, given the similarities in the SNR distribution. And as I said, for the cross correlation, we need to know what is the beam shape through which enter in the cross correlation through this in the cross correlation error calculation through this W factor. And so we went and looked at localized events that are reasonably well determined, and try to see if a 2D Gaussian approximation can be good. And we find that for the HL-VIK, this is a good approximation, while for the ET2CC, it will have more elongated localization errors, which won't really affect too much the final results, but can be fully included in the formalism. So once we define the beam shape, then and fix that as a circular Gaussian beam, we can then convert the 5% confidence level localization area given by bias star on all our detectable events onto the circular Gaussian beam width, and we can get an estimate for each detectable event of the Gaussian beam width as a function of redshift, and this is what you see here for the HL-VIK configuration of detectors for binary black holes and binary neutron stars, where you can actually see that the points that are here in this parameter space are kind of well localized for low redshift, where you have, of course, higher signal to noise ratio, while at the redshift of about 0.5, the quality of the localization just get worse. But what you can do, and what we have done, is to apply some quality cuts on the localization, and so remove events that are poorly localized. And if you think about the future of the gravitational wave detection pipeline, this is also what you will be able to do, to make quality cuts on your events in order to remove the ones that are not good for the purposes of your analysis. So in the case of binary black holes, we remove about 50% of events that have a localization, say a Gaussian beam width larger than 5 degrees, while for binary neutron stars, we eliminate like 20% of the events. And what you can see here is a dashed line in red is a kind of interpolation with a linear relation, just to check what would be the correlation, if any, between this beam width and the redshift, and to use it, that may be useful also for future purposes. So while for binary black holes events, there is kind of trend, of increasing trend of the beam width as a function of redshift, for the binary neutron stars, this is not the case. And this really boils down to the SNR distribution of your detectable events. If we look in the same way at the binary black holes, so for the third generation detectors, then we would see then there is again a strong correlation between the beam width and the redshift, that those events below redshift 0.3, which are almost complete, are very well localized, with beam width that are of the order of fraction of degree, and that there is only 1% fraction of the events that is only poorly localized, and we can again get rid of it by quality cuts. So and as I was saying, the fact of having very well localized events depends on the signal to noise ratio distribution. So this is the number of beams as a function of signal to noise ratio for the detectable events with the third generation detectors, where you can see that while for binary black holes, basically you have that the peak of the distribution is at higher signal to noise ratio. So it means that the third detector configuration will be able to see with an increased signal over noise ratio basically the objects that he have seen at the threshold of detection with the 2G detectors. For BNS, this is not really the case. So even for BNS, BNS would look at the threshold of detection for the third generation detectors. And this means that there will not be many differences in terms of qualitative features in those kind of positional errors that you can have between let's say 5 detectors at the second generation and 3 detectors of third generation. And this is because the localization error really depends on the SNR. The stronger is the SNR, the better is the localization uncertainty. So then coming to galaxy catalogs, I just recall that the galaxy catalog, the cross correlation depends on the intensity, depends on the window function, and the error on the cross correlation depends on the sky coverage and the shot noise. So there are 2 main requirements that a good galaxy catalog needs to have in order to be a good tracer for a positive cross correlation. So in order to increase the intensity of the cross-angular power spectrum, it has to have a good overlap with the gravitational wave detectable events. And in order to reduce the error on the cross correlation, then we want a large sky coverage and a large number of galaxies. So then we have used for our projections either current catalogs and both current catalogs and future catalogs. So for the current catalogs, we have used the 2-mass photometric redshift catalogs. So this 2MPZ catalog, which is a shallow catalog which extends up to redshift of 0.2, which has an almost 70% sky coverage and contains about 10 to the 6 galaxies. You then have the WISE SuperCosmo catalog, which is peaked at around redshift of 0.2 and extends up to redshift 0.4. Again, has a similar sky coverage of the 2-mass one, so 70%, and a slightly, a much higher number of galaxies, which reaches up 10 to the 7. And finally, you have the SDSS photometric catalog, which has a tail up to 0.7 in redshift, but has a much smaller sky coverage, only 20%, and a similar number of galaxies as in the WISE SuperCosmo. Yeah, thank you. So, as I said, the Windows choice of the window function of the catalog is important because it defines you need to have a good overlap. So here, just to show you that the 2-mass catalogs and the WISE SuperCosmo would be good tracers of a cross correlation with binary neutron star and binary black holes neutron stars, while the SDSS is better suited to find cross correlation with binary black holes for 2G detector configurations. The Euclid photometric catalog is an example of a future catalog that we have been using to make cross correlation with the 3G detector configuration. This is will be peaked at around 1 in redshift space with a tail up to 3 as a 40% sky coverage and about 10 to the 9 galaxies will be discovered. There are other catalogs that we haven't really been using for our forecast, like the Vera Rubin LSST photometric catalog and the SPHERIX, but we do expect similar performances as the Euclid one. And in order to look at how does the window function for this future catalog match the 3G detector configuration, we see that this will really fall in the peak of the distribution. So now coming to the results in the 5 minutes that I've left. So what I want to show here are actually the result on how we would be able to cross-correlate and to detect a positive cross-correlation with the different binaries. So here is the angular power spectrum, cross-correlation power spectrum as a function multiple for different binary classes and for HLV and HLVLK. where we see that the two-mass catalog will actually provide the best performances. And this comes from the fact that it really offers a very good superposition with the redshift distribution between the galaxy catalog and the binary events, in which HLVK we are already will be in the reach of detecting a positive cross correlation between those two class of binaries and galaxy catalogs. So we can also quantify how good, what is really the signal detectabilities in terms of sigma. And for this, we run basically a chi-square analysis where we compute what is the difference in chi-square with respect to our reference model. And we can use this delta chi-square to compute the 1 sigma error on the determination of the bias. So we want to know what is at which precision we can measure the bias. But also we can use the delta chi-square with respect to b equal to 0 to get quantify the statistical significance of the cross correlation with respect to the isotropic sky. So if we do so, then we get this table where for different galaxy catalogs and different binary populations for different detector configurations, we can get the significance of a positive cross correlation that we may be able to detect. And as we can see here, for binary neutron star and binary black hole neutron stars, which 5 detectors of 2G, we can be able to detect a positive cross correlation at more than 5 sigma with the 2-mass catalog. While already with perhaps already a detection at 3 sigma is in the reach of HLB. Nonetheless, if we look at binary black holes, then the detection prospects are quite poor. And this is because the redshift distribution peak at quite high redshift. And so the anisotropy that you would expect is small given this geometrical effect of the volume, which is involved. So more events are needed, or rather you can have a tomographic approach. And to do this means that what you actually do is to divide your events in several redshift bins and try to exploit the redshift information. So if we look at then binary black holes for the 3 detector configuration, we can do a tomographic study for, again, all the detectors configurations, having different number of bins. And you can see that on the one hand, for HLV and HLV-IK, tomography is really crucial to get good signal to noise for the detection of a positive cross correlations for binary black holes. And this will be especially striking for the 3G configuration, where you can reach significances of the cross correlation of binary black holes and large scale structures at already, more than 20 sigma. So tomography is really crucial to get an improvement of the detection capabilities of binary black holes and cross correlation with the large scale structure. And finally, we also have investigated how well you can reconstruct the bias. And this is especially important in order to understand if you can really discriminate formation scenarios for binary black holes. And so here you see the bias as a function of redshift and the precision that you can achieve for a single bin analysis. Here in red, which is for HLV-Chi about 20%, for redshift less than 0.3, and is an error of about 10% if you do a combined analysis of all the bins. And the same for the 3rd generation scenario, where you have can achieve like errors which are typically below 10% at low redshift, and a few percent if you then consider the combination of all the bins. So to conclude, we have run a full simulation of the detectability of combat binary mergers for specific detector configurations, accounting for detector effects and localization error. we have used the current and future galaxy catalog specifications, which are close to realities, and we've shown that in order to get the maximum out of this cross-correlation business, you really have to maximize the overlap in refuge distribution and exploit a tomographic approach. So the conclusion is that with HLVIK, you can be able to detect a cross-correlation at more than 5 sigma for binary neutron star and black hole neutron stars with already available galaxy catalogs. And even perhaps the 3 sigma signal for BNS is in the reach of HLV. For binary black holes, the tomographic approach is really crucial in order to give you already like a 5 sigma detection with 5 detectors of 2G generation. And the bias that you can, the precision at which you can reconstruct the bias is of the order of 10 to few %, depending on which kind of detectors are you using. And with this precision, you may be able really to discriminate different models about the origin of binary black holes, but also to probe if present evolutionary effects in the bias evolution with redshift in order to discriminate different astrophysical scenarios for binary black hole formation. And finally, let me mention that all this work really is independent of the inclusion or not of the electromagnetic counterpart information, which can, on the other hand, enhance the sensitivity to binary neutron star and binary black holes. So thank you for the attention. And I'm happy to take your questions.
Thank you very much for the nice talk. We can have questions. Okay, I see Lam Hui raised hand, so maybe we can have his question first from Zoom.
Hi, thank you very much for the nice talk. I have 2 questions. One question is, I think it's somewhere in the middle of your talk, where you have a plot of the redshift error versus the signal to noise for the events. Yeah, that plot. And the plot on the right, as you said, there are somehow 2 modes. You know, some of the events for the redshift error actually decrease, basically inversely proportional to signal to noise, but there are some that do not. For a given event, what is the factor that tells you which one you belong to? What makes the difference?
So I think this really depends on the SNR of the binaries. So you see that this is bimodal. So as you said, so there is a limit where then they are kind of similar, but it is when you have very local objects with high SNRs that then you have this scaling of 1 over SNR. So this will give you a handle which of the 2 modes you are following. So events that are far away from us then will actually have an SNR which is almost independent of redshift.
I see. So if I fix a given SNR, so there are 2 kinds of events. It looks like some that have much smaller redshift error than the other. Is the main difference how good the localization is?
Yes.
Okay. The second question, which is probably pretty quick. You have this nice table, a forecast that tells us with future experiments, how many number of events we expect to get. As you also emphasize, one could cross-correlate either with the events or with the stochastic background. Can you give us a sense with these future experiments, how likely we are going to be able to measure the stochastic background?
Through cross-correlation?
Well, to measure the cross-correlation between the galaxy catalog and the gravitational wave background, I guess we need to be able to see the gravitational background to begin with. And I guess my question is, how likely we will be able to see that?
Yes, then I'm not really an expert on the prospect for detection of the stochastic gravitational background, but let me perhaps mention that what I know is that with third generation events, these astrophysical gravitational wave backgrounds will look quite different from what it would look like in 2G detectors, because in that case, you will basically have that events will form like more sort of popcorn noise and will be mostly resolved. So then I think you can really exploit cross-correlation with future instruments in order to try to get a sense of the possible cross-correlation of this astrophysical background with galaxy catalogs, while backgrounds that would be more of cosmological origin would have a different type of time series. So it would be really look like a correlated noise between detectors.
Okay, thank you very much.
Okay, and any questions from the room? Okay.
Very faint, not so much loud. So.
Better?
And now it's better with
Yeah.
the microphone.
Okay. Yeah. Hi. This is Stefano. So nice talk. Thank you very much for the presentation. I have a question, but if you already touched upon that, sorry if I missed it. You're saying you're not relying on any electromagnetic counterparts for your gravitational waves, right? So you're just doing the cross correlation blindly, really like projected in the sky, like with continuum galaxy, let's say. You are assuming though a distribution for these black holes, the redshift distribution of the objects. In your analysis, you are allowing for unknown parameters for the bias, etc. Are you also taking into account the uncertainty in the distribution of these objects, like parameterizing it some way, or you assume you know that, and it's just you can't slice it up into redshift bins?
So for you mean about the mock catalog generation, right? What are the uncertainties in the parameter space for the population that we explored? And I mean, we do kind of we don't do a systematic exploration of all the uncertainties related, for example, to the star formation rate or the time delay that you will have in the merger density or the local rate. So we do kind of convolve, we do a Monte Carlo simulation, which some fixed PDF, but we don't explore thoroughly all the systematics that you can have in the, for example, star formation rate.
Okay, yeah, that's very much uncertain. So a possible way out of this would be just, I don't know, you have this probability distribution function from where your objects will be in redshift that come from this complicated astrophysics and integral and star formation rate, etc. You don't want probably to fit for that because the information is too little. What you could do is like to fit like a template to the distribution, some sort of, I don't know, exponential cutoff plus some power law, and then trying to fit for the parameters of that template, seeing how much your final result is dependent on the assumptions given in an agnostic way of putting the problem, let's say. Could be interesting to see.
Makes sense. It would be like how you can make a model inference with the cross correlation. Basically.
Yeah, some sort of taking into account the ignorance about the distribution of these objects.
Thank you.
I also have a question. Regarding the nonlinear matter spectrum, do you change the recipe depending on where you have the redshift distribution? For example, for very low redshift, you have a halo occupation distribution, and then you have another modeling for the nonlinear, for Euclid, for example?
No, I don't think so. I think we use
the same?
Yeah, we use, I think so.
Okay, it should be halo model, something like that, right?
Yeah, I think it is with we do that both with halo model and with class, but
okay, thanks.
Checking that they are comparable.
Okay.